Today we are going to talk about section 2 of chapter 12, which is about vectors. Before we jump into the PowerPoint, I'm going to use a video clip to remind you what a vector is.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
All right, so that's vector, and he is exactly right about what a vector is. A vector is a mathematical quantity that we represent by an arrow, and it has both direction and magnitude. So this is the directed line segment that goes from the initial point A to the terminal point B. There's an arrow there to show the direction from initial to terminal. So that's the direction. The magnitude is the length of the vector. So a vector has both length and direction. These are commonly used in physics to represent forces and other concepts like velocity. So we could have a two-dimensional vector, but we could also have a three-dimensional vector where we're talking about a particle moving through space. Instead, two-dimensional would just be moving through a plane. So these are four different vectors here, and they actually all represent the same vector amount. So a vector's two features are its magnitude and its direction. So if those two features are the same, it actually doesn't matter where the initial and terminal points are for the vectors to be equivalent. So all four of these vectors have the same direction. Direction we can think of like slope or like an angle. They all have the same slope or angle, and they all have the same magnitude or length. So these four vectors are all equivalent. The one that's named OP there is going to be an important one for us. It's called the component vector, and that it originates at the origin. So a vector is represented by a directed line segment, like AB there with the arrow above. Its length, we denote by putting absolute value around it. It looks like the absolute value symbol there. That means length. So it doesn't mean make it positive. It means the magnitude or length of that vector. And two vectors, again, are equal if they have the same length and direction. So this could be a three-dimensional vector here. Where we have three component parts to it, like an X, a Y, and a Z. Now notice on in the middle there where it names the vector V with kind of the boldface V, and then it has the brackets that are like more triangular rather than rounded. That is to imply that it begins at the origin. So when you see a vector with those, that is to imply that it begins at the origin and it ends at that point V1, V2, V3. That's the terminal point with it originating at the origin. It is equivalent to the blue vector that's there as well, just that one is not in its component form. That one is not originating from the origin. So we have our two-dimensional or three-dimensional forms of this. Again, we call it the component form when it starts at the origin, and then what's given in those more kind of pointy brackets are the terminal point coordinates. Magnitude or length we can find with a Pythagorean theorem. So we talked about length in the last section. This is essentially the same thing here, that we can find the magnitude or length by looking at the distance between the originating point and the terminal point. Okay, this is actually a diagram for an example that we're gonna do. Let's we'll go ahead and switch over and look at some examples, and we'll kind of flip back and forth today, I think, for some of those different pictures. So the first example that we're going to do, actually, we will look at component form and we will look at length. So I'm going to start with a vector that originates at point P at -3, 4, 1, and terminates at point Q, so -5, 2, 2. And so we're going to be looking at the vector PQ, originates at P and terminates at Q. First thing I want to do is put this into its component form. So to put it in its component form, what we want to do is take a vector that's going to have the same direction, it's going to have the same magnitude, but that it starts at the origin instead of starting at P. And three-dimensionally, it's a little bit harder to understand just because graphing in 3 dimensions a little bit harder to see what's going on. So I'm going to side note and look at what if we were just dealing with 2 dimensions. So we'll say P is -3, 4, and Q is -5, 2. If I plot out this vector, 1, 2, 3, 1, 2, 3, 4, there's point P, and -5, 2, there's point Q, there's vector PQ. Now what we want to do is we want to translate this over so that it originates at the origin. So we want P to relocate itself at point 0, 0. So think about, well, how would I do that? To do that, I'd have to, on my x-axis, I'd have to move over, well, P's at -3, so I'd have to go over 3 spots. And then if I do that with Q as well, 1, 2, 3, because I want to keep everything the same. So now we're looking at 1, 2, 3. There we go. Now we're looking at the x coordinate being at -2. So vector V is going to have an x component of -2. And then we want to say, well, what's happening to the y? If I want to move P down to the origin, I would have to go down 4 spots. So I need to do that here as well, go down 4 spots, and that's going to put point Q at -2. So vector V there in its component form, -2, -2, is equivalent to the vector PQ because it has the same direction and it has the same magnitude. And direction we can think of as slope. So the slopes of those two are the same and the magnitude is the same as we translated it over. So back to our example in 3 dimensions, we can do that same thing to move all of the points on over. And graphing, again, in 3 dimensions, a little bit trickier to think about, but we could do this with a subtraction. So we're going to go -5 minus -3, taking terminal minus initial. So I want to do terminal minus initial here. So -5 minus 3, the x pieces, and then 2 minus 4, the y pieces, and then 2 minus 1, the z pieces. So vector V is going to be -2, -2, +1. So that's the component form of the vector then. So this would originate at the origin, terminate at the point -2, -2, 1, has the same direction and magnitude as the original vector PQ. So that's component form. And then magnitude. If I want to find the magnitude of vector V, we're going to use a Pythagorean theorem, and we can do that on the component form. So -2 squared, -2 squared, and 1 squared. Make sure you're using those parentheses because squaring a negative does make a difference for the sign. So that's 4 plus 4 plus 1, which is 9. So that means the magnitude of this vector is 3. Okay, so that is component and magnitude. Okay, so now I'm going to jump back over to the slide here and take a look at this picture. So in this picture, it's a word problem setup. We have a cart that is being pulled along horizontal ground, and it's being pulled at a 45-degree angle there as depicted in the picture. And it doesn't show it in this picture, but it's being pulled with a force of 20 pounds. But what we want to know is what is the effective force? So really, we're not trying to pick up the cart, we're trying to pull the cart, essentially, we would think, along this horizontal ground to get it to a new location. And so we might be pulling on that blue vector with a force of 20 pounds, but some of that force is exerting upward, which is kind of like wasted because we're not trying to lift the cart. So we want to know what is the effective force or the horizontal force in this. So I'm going to flip back over and we'll look at the whiteboard here for this. So if I have just kind of a resketch of this, we got our cart. We want to know what's happening in the horizontal direction. We know there's 20 pounds of force in the diagonal at a 45, but what we want to know is what is the x component of that force, or the x value in that. So what we're looking for is what is the horizontal force on this. So we made a right triangle there. So right triangle, we can use trig. So x is the adjacent. So we'd be talking about the cosine of 45 is adjacent over hypotenuse there. And so we get 20 cosine of 45 is x, or our horizontal force on this. So we get 20 over a square root of 2 is our x if we're going for exact values, or we could divide that on out, and we find it's about 14 pounds. So we're pulling with a force of 20, but only 14 of those are actually acting in the direction that we want them to move our cart along the ground. Okay. All right. All right, so if we have two vectors, u and v, both in their component forms there, we can add them together by adding together the like components. So add together the first part with the first part, second part with the second part, third part with the third part. To use a scalar multiplication, we can multiply that through. A scalar is just a constant number, like a coefficient. It's going to change the magnitude of the vector, but it will not change its direction. And it's not a vector. So it's not a vector times a vector. There's actually two different ways to do that, called the dot product and the cross product. This is just taking a number, a single number, multiplying it through, and you just distribute it through to each part. The geometric interpretation of adding vectors. So in that first one, we have vector u and vector v in what we call a tail to tip formation. So vector u drawn first, and then vector v drawn originating at the terminal point of u. Then if you go from the originating point of u to the terminating point of v, that is equivalent to the sum of those two vectors. So that's what we call our tail to tip drawing there. In B, we have both of them in their standard form. So if we wanted to redraw them then in that tail to tip, that's what those diagonal lines would be. And that we could take vector v and kind of move it over so that it originates at the end of u and give us then that u plus v vector. You'll have some problems that ask you to kind of visually think about relocating them tail to tip and what would that sum be. For a scalar multiple, if we multiply up at the top there, it shows u is the original, the blue one. If we multiply by 1.5, same direction, but 1.5 times as long. Or if we multiply by 2, same direction, but 2 times as long. Now if we multiply by -2, it's kind of the same direction, but it reverses the direction. So same angle direction, but negative backwards, and then doubles the length as well. So multiplying by a positive scalar only changes the magnitude. Multiplying by a negative scalar would change the magnitude and it reverses the direction. So we can also subtract vectors in this tail to tip idea, in that instead of translating, so in part A there, that u and v are both originating at the same point. If we want to redraw it in the tail to tip idea, In part B, we take vector v and we put it at the end of u, but instead of v pointing upward, we switch it to have a negative direction and point downward, and then we can find our difference vector there in the pink. Okay, so then we'll switch over and look at how to do some component-wise addition and subtraction with vectors. Okay, so let's say that vector u is -1, 3, +1, and vector v is 4, 7, 0. If I wanted to find 2u plus 3v, I'm going to take vector u and I'm going to double each part, distribute the 2 through. Then I'm going to say we are adding that to 3 times vector v. So now I'm going to distribute a 3 through vector v. And then for my final answer, I'm going to put together these two vectors component-wise. So I'm going to put together the first piece with the first piece, that makes 10. Then the second piece with the second piece, that makes 27. And then lastly, the last piece with the last piece, and that makes 2. And so that would be our final answer to the sum of 2u plus 3v. Okay. If I wanted to find 1/2 of u, and then remember that those absolute value marks on it mean the magnitude. So remember, multiplying by a scalar only changes the magnitude. So this is actually going to take the magnitude of u and cut it in 1/2. So you have two options. You could either just find the magnitude of u and cut it in half, or you could distribute 1/2 through vector u and then find the magnitude of that. Either way, doesn't really matter. I'm going to do the distributing way. So I'm going to distribute 1/2 through the vector u. So that's -1/2, 3/2, 1/2. And now I'm going to find the magnitude of that. So the magnitude of, oh boy. Okay, your screen still looks good. Mine just turned into a disaster. So, okay. Magnitude is going to be -1/2 squared plus 3/2 squared plus 1/2 squared. So that's going to be a 1/4 and 9/4 and 1/4. So that is square root of 11/4, or we could say square root of 11 over 2 there. So that would be our magnitude of 1/2 of vector u. Okay. All right. So those are same examples. There's also a subtraction one here in the slides. To subtract, you do the same thing, just subtract component-wise. So some vector operations. Adding vectors is commutative, which means u plus v equals v plus u. It's also associative, which means that if you're adding 3 vectors together, you can regroup and add together these 2 or add together these 2. So it tends to follow, vectors tend to follow our same properties as our real numbers. Okay. I, j, and k are what we call our unit vectors in each direction. So I is the unit vector of the x, and then j is the unit vector of the y, and k is the unit vector of the z. So we can write a vector as, looking for like a final, I don't have a final name here. We could put it in those little brackets, and we could say that it's like x comma y comma z. Or we could say that it's xi plus yj plus kz. So we could take what's in these and then just give an I, a j, and a k to each piece. And we'll look at an example of that. Okay, So we'll go ahead and look at an example of that. All right. So I'm going to say point P1, this is going to be our originating point, is 1, 0, 1. Point P2 is going to be 3, 2, 0. And we're going to find the component form vector for P1 to P2. So we'll call it V. And so as we did before, to find our component form, we can take the difference, end minus beginning. So 3 minus 1, 2 minus 0, and 0 minus 1. So our component form for vector V is going to be 2, 2, negative 1. Okay? That is the vector that would begin at the origin and end at the point 2, 2, negative 1, but it has the same direction and same length as the vector from P1 to P2. Now, this vector does not have a length of 1, so it is not what we would call a unit vector. A unit vector has a length of 1. So if I want to find a vector with a length of 1 that goes in the same direction as this, turn it into a unit vector, what we need to do is find what is the magnitude of this vector. So 2 squared, 2 squared, negative 1 squared, all under a square root. That makes 9, which is 3. Then square root of 9 is 3. So the unit vector that's in the same direction as V, but only has a length of 1, would be 2/3, 2/3, and negative 1/3. So it has the same values as the vector V, but then dividing by that 3 to cut the length down, so that now the length is only 1. Okay? If I wanted to name this vector using the I, J, and K, we could call it then 2/3 I plus 2/3 K minus 1/3 J. So we just take each piece of it and assign the letters I, J, K. Two different representations, they mean exactly the same thing. So if you see a vector with those triangular brackets, that means exactly the same thing as a vector named in IJK form. Right? These two both happen to be unit length. Doesn't have to be. Seeing the IJ and K doesn't mean that it's unit length. These both happen to be unit length. But the IJK just means that those are each component piece of a vector. Just a different way to name it. Okay, we are going to look at another example. In this one, velocity. We're going to have a velocity vector that is 3i minus 4j, just a two-dimensional velocity vector. And what we want to do is we want to rewrite this as its speed. So we're going to rewrite as speed times direction. Well, if we think about what speed was, speed and velocity, those are a lot the same, except velocity has direction and speed does not. So what we want to do for speed, if I think of, I could have a velocity of 30. That means I'm going a speed of 30 in some direction. Or I could have a velocity of negative 30. The speed would still be 30, just in a different direction. So speed is the absolute value of velocity. Absolute value, we've been saying, is magnitude. So what we're going to do is take the magnitude of V. Well, magnitude is length, so we're going to find the length here. And that would be 9 plus 16, that's 25, and the square root of that's 5. So the speed, if this is a velocity vector, the speed is 5. So 5. Now, if I want it to be speed times direction, but it has to still be equal to that same vector, because we don't want to change it, we're just rewriting. Velocity is speed times direction. What I want to do is divide a 3 out of this. So, divide a 5 out of this. So I'm going to say 3/5 of I minus 4/5 of j. Then if I distributed the 5 back through, it'd be exactly equal to where we started. So we haven't changed it, but now we've broken it down into what is the speed, 5, and what is the direction. It would be in the same direction as that unit vector. All right. One more problem, and I think there's a slide to illustrate it. This is the problem we just looked at. One more problem I want to look at here. All right, so it's going to be a word problem. We're going to have an airplane. The airplane has a speed of 500 miles an hour heading due east, but then it encounters some wind. The wind is going to have a speed of 70 miles an hour, and the speed is coming in at 60 degrees north of east. And what we want to figure out is what happens to the plane. So when this happens, what happens to the velocity of the plane and the direction of the plane, speed of the plane. So our plane sets its heading due east at 500 miles an hour. So the plane has a vector of 500, 0. That's the plane's intention, just all x direction. But then it encounters this wind. This wind comes in at 70 and 60 degrees north of east. Now that 70 degrees is on the diagonal, so part of it is in the x direction, which is going to kind of push the plane along, but part of it's in the y direction, which is also going to push our plane up and off course a little bit. So what we want to do is figure out how much is the x and how much is the y. So trig, because this is a right triangle. So the cosine of 60 is going to be x over 70, or x is equal to 70 cosine of 60. That's the x component of the plane. Now for the y, sine is opposite over hypotenuse. So y is going to be 70 sine of 60. That's the y component of the wind. I think I said the last one was the plane. I meant the wind. So in the blue there, we got the wind, the x, and the y components. Now, the wind is actually going to be added to the plane. So then we could think about doing that tail to tip thing and actually translating that vector over here. And then the final sum is going to be the new direction and speed of the plane there, which can be found by adding these two vectors together. So now, let's see, 60 degrees, we got 1, 2, and square root of 3. So cosine is 1/2. So this is actually going to be, I should do it in blue. It's going to be 35 there for that cosine. And then this is going to be, let's see, 70 square root of 3 over 2, or 35 square root of 3, I guess I can simplify it down to. So then when I add those together, I'm going to get 535 and 35 square roots of 3. So that tells us now what the x and the y components of them are. So if I wanted to know the speed would be the magnitude of this. So if I didn't grab my calculator, so I can't actually do the final calculation here because I don't trust myself to do this in my head. But I could type that into a calculator, and that would give me the final speed of the plane in its new direction. And if I needed to find the new direction angle of it, then what I would be looking for back on my picture here is theta that I just drew in there in green. And we would know in our green triangle now, we've got 535 there. We got 35 root of 3 there. And what we're looking for then would be a tangent of what angle is 35 root 3 over 535. And we could do an inverse tangent on that, and that would give us our new angle, which would give us kind of our new compass heading and how far off course is this plane. Okay, so that is the end of this lesson, and that's actually going to be the end of chapter 12 for us. There are several more sections here in chapter 12 about dot product and cross product and other physics applications of vectors and lines and planes in space, doing more three-dimensional graphing and such, cylinders and quadratic surfaces. That's really getting into some good three-dimensional graphing stuff there. But like I said, we're just trying to intro this. If you go on and take Calc 3, multivariate calculus, you'll get into those surfaces and other applications a lot more. So here, just kind of wanted to introduce this. So ask me whatever questions you have. I hope you have a great day. See you later.